Hello everyone, so welcome to our seminar today. So the speaker today is Professor Regina Burachik from the University of South Australia. So she's an Argentina mathematician who got her PhD from the AMPI in 1995 with the title Generalized Proximal Point Methods for Rational Inequality Problem. And since then, she became an expert in many aspects of optimizations. So there are many things I want to talk about Regina, but probably people come here for her talk. So now I will pass the stage to Regina.
What? You didn't say that Regina is actually an Australian mathematician. Maybe you don't know that.
Australian and Argentina.
Well, we live in a universe now. So I think one contribution of coronavirus is that it made us forget about frontiers, and we are all together in the same boat, right? It became a bigger boat than it was before. So welcome everybody. Thank you very much for coming to my talk today. And I will speak about a primal-dual penalty method via rounded weighted L1 Lagrangian duality. So this is a joint work with Yalchin Kaya, who is present, and Chris Price from University of Canterbury, New Zealand. And so the topic of the work has to do with a special type of duality framework for non-convex optimization problems. I will show how we set up this framework by means of a sequence of dual problems, not the usual way of a single dual problem associated with a primal problem, but in our situation, we will associate a sequence of dual problems to a single primal optimization problem. And also we will devise for this particular type of framework a search direction that can be currently changed and used for each of the current dual functions. So we will devise, besides from a search direction, a stopping criterion as well. For that particular type of procedure, we will present our convergence analysis in which we show that the dual values come to the primal optimal value. We will discuss the situation of having finite convergence, and we will precisely state our primal convergence results. I will end up the talk with numerical experiments, and I will present 3 non-convex numerical experiments. I want to say from the very beginning that the structure of this talk is half of the talk is going to be theoretical, and the second half is going to be showing the numerical experiments. So the structure of the problem we consider is very general. So minimization of a function subject to an abstract constraint, capital X, and equality and inequality constraints. So all the functions involved are assumed to be continuous, and the primal variable is supposed to be in a certain metric space, and this capital X, this abstract constraint here, is a compact subset of that metric space. So I want to emphasize that this could go for infinite dimensional situations. However, to avoid complexities in the analysis, we assume the compactness of this capital X. And to also avoid trivial situations, we suppose that we assume that the feasible set X0, which we denote as X0, is not empty and it is not the whole space. The optimal dual value is denoted by capital MP, and the set of points in capital X which are feasible at which that optimal value is attained is called a star. So I will refer to MP during my talk. I will refer to X0 during my talk as the set, and also to a star. So of course, and a typical approach, especially a typical approach to deal with these inequality constraints here, is the so-called penalty approach, in which you penalize the violation of the constraints. And the famous L1 penalty function that you would use typically for a problem like problem P is a penalty in which you have the objective function, and then you have a penalty multiplier, positive, multiplied by the violation of the equality constraints in the form of the absolute value of those equality constraints, plus a penalty parameters times the violation of the inequality constraints. So the violation of the inequality constraints is measured by this function, the maximum between the argument and 0. So this is the typical L1 penalty function that you would use if you could. However, in some situations, the problem P is a smooth problem. And in that case, you would be a little bit reluctant in using L1 penalty. Why? Because you would destroy a very good property of your problem, which is smoothness. And I want to emphasize that this smoothness may happen together with situations which are very common in applications. For example, you may have a problem which is an integer programming problem, linear integer programming problem with constraints 0, 1, in which you have the equality constraint x times 1 minus x equal to 0, which is the integer constraints. So that gives you a polynomial equality constraint that you may not want to deal with. And in that case, you would like to preserve the smoothness of the problem, but at the same time, you would like to address that constraint in a very in a way that gives you a solution which is feasible, right? So this type of problems in which the problem is smooth, but you still have a very high level of complexity is a very important type of situation. So this is precisely the aim of this paper, to devise a penalty approach that can deal with those type of constraints, but at the same time it preserves the smoothness of the original problem. And we do that by means of two functions. Some of you might immediately recognize these functions, some of you may not, but I will remind you later on the reason for this. Take any w positive here or 0 and define eta, the function which is this quadratic function between minus w and w, and a vertical shift of the absolute value for larger values of t. So this function was presented in the last week by Chris, who is just here. And also we consider the function gamma, which is similar to eta in the non-negative for variables, and 0 for all negative variables. So let me just show you the situation. So let me just, this is minus here. So this is the absolute value, and this is the function eta, and this is the rounding region where you have this quadratic part. So this part was explained by Chris in the last week, which is a smooth approximation, a smooth minorant of the absolute value. And a totally similar argument goes for this function, which is the penalty for the inequality constraints, in which you do the same type of vertical translation of the absolute value, but only for the non-negative variables. And in that region is where you obtain the quadratic part. So these are the functions eta and gamma that helps us in the smoothening work that we need to do. And the function eta is also known as the scaled Hoover function, w, and inside that round it behaves like the absolute value. And as I mentioned before, it is a smooth minorant of the absolute value. And for small values of w, the rounding region becomes smaller and smaller, and therefore the function becomes closer and closer to the absolute value. Exactly the same reasoning goes for the function gamma, and just wanted to remind that the function eta can be obtained through convex analysis as the infimal convolution of the absolute value and a quadratic, the absolute value and the quadratic polynomial I showed before. And for those who remember Jane Shan Chen's talk his variational analysis seminar from August 26, he presented this and many more beautiful examples of smoothing functions. And so I invited all those who are interested in the use of convex analysis for smoothing of functions, please go to his beautiful slides. Then from the time being, we'll just concentrate now on the construction of the Lagrangian by means of these two functions, eta and gamma. Now the L1 penalty function, I just want to remind everybody, has these parts here, which are the non-smooth parts, and U and V are the what we call the penalty vectors. Now from the definition, sorry. I wanted to say that now the rounded L1 Lagrangian replaces the absolute value by the eta and the maximum between 0 and the argument by this function gamma. Of course, because of the presence of the rounding parameter w, this w should be present as well in the definition of the Lagrangian. So now the Lagrangian is not only a function of x and the vector of penalties u and v, but also a function of w. Now from the definitions we can see that the Lagrangian, the rounded Lagrangian, is at a distance from the L1 penalty, which can be the distance between the rounded Lagrangian and the L1 penalty can be computed as a multiple of w. So from here you can easily see that when w tends to 0, the LW, the Lagrangian LW, converges pointwise to the L1 penalty. And just a philosophical comment regarding this. So we will look at u and v as dual variables that depend on the process that are going to be updated with in the algorithm, and w is going to be at our service. So we will decide which w we are going to use. So now that we have a Lagrangian, we can define the dual function. And this scheme of procedure for defining the dual function and the dual problem comes totally from conjugate duality of Rockefeller. So Rockefeller already determined how to do this. So once you have the Lagrangian, you take the infimum of the Lagrangian, and that infimum is going to be your dual function. So because we restrict our domain of to have positive vectors of penalty, then we take here we define our function in that domain, and because capital X is assumed to be compact, we can replace the infimum by a minimum. So we have a minimum here, which is always a finite value for every positive vector of penalties. Otherwise, it's minus infinity. So this is our function. Another comment I want to make is that because the Lagrangian is an affine function of u and v, affine function of u and v for x fixed, then this minimum by classical convex analysis is a concave function, because it is a minimum of concave functions. Therefore, this is a concave function. and therefore is going to be continuous and concave wherever it is defined. So it's a beautiful concave function. And the dual problem is also a dual problem, which is a convex problem, because it is the maximization of a concave function subject to a convex set. So we have a perfectly nice convex problem. And we will define this problem as dw because it depends on the Lagrangian and then depends on w. And the optimal value is mdw. So we have, in fact, not a single unique dual problem, but we have like a machine of producing different types of dual problems, right? And what will happen with this machine? While we make W go to 0, this dual problem becomes closer and closer to the dual problem that would have been induced by the classical L1 penalty. So because we don't want to deal with that dual problem directly, we approach that dual problem from below. And let me explain why. Okay, so this will be in a couple of in a couple of slides. There are some things that we can say now already for every W positive. As I mentioned before, we can already say that the problem is the dual problem is a convex problem because Q is concave continuous and the constraint set UV is convex. And moreover, as I mentioned before, all the dual function values are attained because of the compactness of capital X and the continuity of all the functions involved in the construction of the Lagrangian. We can also show weak duality. For every W positive, we can show that the dual values are always bounded above by the optimal primal value, and therefore directly we have that the optimal dual value is always bounded above by this optimal primal value, right? So weak duality comes almost immediately. Now let's look at what are the other things that we can conclude. As I mentioned to you, our idea was to take the sequence WK tending, being decreasing, not tending to anywhere in particular, but because the WKs are positive and decreasing, for sure they will converge somewhere, right? And just for economy of notation, we will call LK instead of LWK, and we will use DK instead of DWK. Now we have a sequence of functions, the Lagrangians. We can show that while WK decreases, the Lagrangians increase. They are all bounded above by the L1 penalty. So this is a sequence. Tells us something with respect to the sequence of functions. Now there's also something to say about the sequence of optimal dual values as a sequence of numbers. So the optimal dual values also provides us an increasing sequence bounded above by the primal optimal value. Now when W happens to go to 0, then the sequence LK of Lagrangians converges pointwise to the L1 penalty, and this is something that I already mentioned. And if WK is just a decreasing sequence, then we can show that the sequence of optimal dual values converges to the optimal primal value. And this is the important part of the result. This is what we are going to use in our analysis. That when we get the optimal primal value, when we get the optimal dual values, that makes sense. Why? Because when W decreases, those values get closer and closer to the optimal primal value. So this justifies solving the sequence of dual problems. And for that, what we need mainly is to find a valid search section for each of the current sequence of dual functions that we generate. We construct a vector which vector that measures the infeasibility of my point x. So let's construct the vector p eta, and this p eta has nothing but the value of eta at each of the equality constraints for that particular value of w. And this vector kind of measure of the violation by x of the equality constraints. Because if, for example, if x verifies this equality constraint, then this coordinate is equal to 0. But if it violates that constraint, then this coordinate is strictly positive. Therefore, the size or the norm of this vector is a measure of x's violation of the equality constraints. In a similar way, we construct this vector p gamma with the gamma values of the inequality constraints at x. And this will give me a measure of x's violation of the inequality constraints. Overall, we can construct the overall violation of x of the constraints by joining these two vectors. And for a fixed u, v, and w positive, we do the following. Suppose that for this u, v, and w, you take the corresponding Lagrangian and you produce a minimizer of this Lagrangian. Just for economy of notation, let's call this Lagrangian x hat. If you compute p at x hat for this value of w, it is a standard fact from convex analysis that this vector p is nothing but a supergradient of qw of uv. By supergradient, I'm using supergradient because qw is concave. So I cannot use the word subgradient because the supergradient stays above the graph of the concave function. So this is a supergradient, and for which this is a supergradient is because x hat is a minimizer of this expression. And the other reason is because if you differentiate the Lagrangian with respect to u and v, what you get is precisely this vector p, because the Lagrangian is affine on u and v. Anyway, so by using some standard convex analysis, you can see that this vector p is a supergradient of qw. However, you can see a little bit more than that. Let me explain you how you deduce a little bit more information from this vector p. Now, suppose that just for more economy of notation, let's call this vector of penalties, call it z, and take a vector pi 0, any non-negative vector of the same size, pi 0. And if you take x hat as before, minimizer of the Lagrangian, then you can show that p of x hat w plus pi 0, so you deflect that direction by a non-negative vector pi 0. That new vector is an epsilon superdifferential of qw at the point z. But not for every epsilon, of course, for epsilon larger than the scalar product between z and pi 0. So this means that when you minimize your Lagrangian, you get a machine that produces you not only search directions that are epsilon, not only search directions which are super differential of qw, but other ones which are epsilon superdifferential almost for free by just adding any non-negative vector. And the proof is standard by using the definition of epsilon subdifferential. And of course, we obtain my previous statement as a direct consequence of this inclusion, because if pi 0 is equal to 0, then here you obtain that this inclusion is true for any epsilon greater than or equal to 0. So you make pi 0 equals 0, and you obtain the differential. This means that you gain a lot of information by minimizing this Lagrangian, right? So let's conclude that this part, that this sum of these two vectors provides us a good search direction for improving QW. So we have the first ingredient for defining an algorithm. The second ingredient is to know where to stop. So to know where to stop, the vector P is also going to be involved in this analysis. And we will see how feasibility is related with optimality in this case. Now, just going back to two slides previously, if we have that the vector P is equal to 0, this means that both equalities and inequality constraints are being verified by your x. And therefore, this means that x is a feasible point. So somehow, this P not only gives me a measure of feasibility, but is going to help us in stopping the algorithm. But before we do that, I need to define one more set, which is the set that is going to define our dual solutions in this particular context. So in this particular context, remember that our dual problem depends on W. So in fact, we don't have a single dual problem. We have a family of dual problems all together. So when we look at dual solutions, we need to involve the parameter W in the definition of those dual solutions. So we will have a dual solution UVW if our dual function QW at UV is equal to the optimal primal value. So in some sense, this gives me an idea of what the exact penalty parameters are going to be. Now, the result that will serve us in devising the stopping criteria is this second box here. So if you take an x hat, which is a minimizer of the Lagrangian, and it is also feasible in the sense that it satisfies all the equality and inequality constraints, then you can show that that x hat is a primal solution and UVW is going to be a dual solution. And in this situation, the dual function at UV is going to be equal to MP because UVW is in SD, and moreover, all the parts in the Lagrangian which corresponds to the constraints will vanish because X is feasible, and therefore it will be equal to F at X hat. So this somehow gives me an idea of what an exact penalty is going to be, because when you minimize, if you have the situation of having x0, then your solution is the solution of the original problem. So in some sense, this gives me what the exact penalty parameter would be in this context when it is also feasible. So this gives me the stopping criterion, and therefore this gives all the ingredients necessary for the algorithm. So in the algorithm, we choose WK decreasing, and we denote ZK, the vector of penalties. So we start with K equal 1, and we take this UVW initial. And step 2, which is the most important step, we minimize our Lagrangian for the current value of WK and the value of ZK. We call the minimizer XK and construct the vector of infeasibilities, called vector PK. If PK is equal to 0, your point is feasible, you can stop because you are at the primal dual solution. If it's not 0, then go to the next step and update. How are you going to update? You are going to update by using an epsilon superdifferential direction, which is the vector of infeasibilities P plus a deflection PK, which is has to be negative, times some positive step size, and then that will give you the new vector of penalties, and then you go to step 2 again with a new penalty and a new parameter W, and that's the whole algorithm. And again, I want to repeat, if the algorithm stops in step 2, you have a primal dual solution, and now you only have to decide to have a more precise definition of an algorithm, who are going to be your step size and which is going to be your deflection. And just want to remind you that in general, for epsilon subgradient and for subgradient method, it is not easy to define a good step size. And for those of you who are familiar with the classical analysis of epsilon subdifferential and subdifferential, you know that in the update of the direction, you can use some analysis which uses like telescopic sum, and so there are always infinite sums involved with the convergence analysis of both epsilon subdifferentials and epsilon subgradient and subgradient method. So there are always some telescopic sums, and so this is not above that condition. So what will happen is that you will not necessarily have a sequence of dual vector zk which will be bounded, but if you do have a sequence which is bounded, this is equivalent to the summability of this series, to the finiteness of this series, and this is equivalent to the convergence of the sequence in this particular case, because all the coordinates of zk are increasing. So let me just go back. You are summing up to zk a non-negative coordinate. Therefore, the coordinates of zk are positive and increasing. Therefore, if they are bounded, they have to converge, right? So this is what happens. So boundedness of the sequence is equivalent to convergence. And another interesting fact is, so I mentioned before that the dual optimal values increase towards the primal optimal value. Moreover, the dual values in this case they increase. We just know that they increase. We will get stronger results later on, but just for every positive step size sk, what we have is that the optimal dual values are increasing, and they are all bounded the optimal primal value. And this monotone increasing is not necessarily strict. Okay, so let's look a little bit at the case of finite termination. This is simple. So as from the very definition of the algorithm, if we have a primal solution, then the algorithm will automatically stop. So primal feasibility without any additional assumption implies or is equivalent to finite termination. Now, in which situations you can say that what you have for some case zero, if you have a dual solution, is the algorithm stopping? Is the algorithm also having finite termination if you have a dual solution at any point k0? Well, what happens is that, or at least what we obtained, is that if you have a positive vector d hat, which is a lower bound of any one of the of every one of the deflection steps. So you see, when you have a deflection step, it means that you have the epsilon supergradient direction. So in this case, if you have this situation, so if every dk is bounded below by a positive vector, and at a point in which you landed on a dual solution, then either you stop at that point or you will stop in the next iteration. But for you to have finite termination, the dual solution, an epsilon subgradient method. So in this situation, under this assumption, dual optimality is also equivalent to finite termination. But I just want to emphasize that this is just for mathematical reasons that we obtain this. What is important in terms of practicality is this part here. And the reason for which we wanted to establish a situation in which we can ensure finite termination also under dual optimality is because in our analysis we use the fact that if we generate an infinite sequence, if the sequence generated by the method is infinite, then we want to be able to say that at no point in the process the xk was a primal solution or the vector of parameters was a dual solution. So that's used in the convergence analysis. Now our convergence analysis is performed for only two steps. So I repeat, for classical subgradient and classical epsilon subgradient, usually the choice of the step size is quite difficult. However, in our case, it's extremely simple. We already have the vector pk because we have computed pk along the process. So we just have to compute the norm of pk to have the step size. So we will analyze two step sizes. One is the norm 2 of the infeasibility vector, and the other one is 1 divided by the norm 2. So these are the two possible choices. And of course, wk, as always, is a decreasing sequence. So for these two choices of the step size, we show that the primal sequence accumulates at a solution, which is in fact the most important result of our algorithm, that it accumulates at a solution, and also the dual values converge to the optimal primal value. So this is the most important consequence of our analysis. The other one is the one that I mentioned to you before. If zk is bounded, then zk converges, and the limit zw is a dual solution. And moreover, if the deflection points are bounded below by a strictly positive vector, we can show that our sequence qk not only converges increasingly to MP, but it is strictly increasing to MP, right? So it pushes, it's like pushing more towards the value. Okay, so now let's go to the numerical experiment. So as I mentioned before, we minimize our function f, and we have equality and inequality constraints. In our examples, capital X will be a subset of a finite dimensional space, compact, and all the functions are differentiable. The method that we use is the subgradient direction, and we will, okay, so this is, sorry, this is the initialization. This is the initialization. The step 2 is going to be the subproblem in which you minimize the Lagrangian and you obtain your solution xk. The step 3 is a step in which you check how feasible your point is, and this is one of the main differences with what I showed you before. You set up here a practical tolerance, and you say you declare your point feasible if this maximum is less than your tolerance. Otherwise, if it's less than your tolerance, you stop. If it's not, then you perform your step. So you increment your variable z by your vectors p eta and p gamma, and here we use no deflection. In the implementation, we did not use the deflection, and so on. So and then you update your vector of penalties, you update your wk, and you go back to step 2. So the remarks, as I mentioned before, this is a pure subgradient method, and in the implementation we only used this step size because it's easy to implement and it's small size in early iterations. The other choice may be too large initially, instability, And the subproblem in step 2 by using the modeling language AMPL, which was paired with the optimization software Nitro, which is a very convenient and famous differentiable solver. So let me show you that in step 2 here, in step 2 is the step in which you do the minimization. So this is the most important step. And I want to emphasize that here in the analysis, we assume that this minimization is done globally, even though in actual facts, you cannot certify that you got a global minimizer because your problem is not convex. And you can use many other smooth solvers for doing this. We used Nitro, but you can use any other smooth solver for solving the subproblems. Now the numerical experiments, in the numerical experiments we solved the problem in two ways. First, we solved the problem directly. We solved the problem directly by using AMPL and Nitro in the conventional way, because Nitro and AMPL, you can write the model and then you can apply Nitro directly without using any algorithm, right? And that's what we call Nitro on its own. And the other way is by using our algorithm. So if you use our algorithm, then you use Nitro only in that step in which you need to minimize the Lagrangian. So the advantage is that you do not need to model the inequality constraints using the software, because you just minimize the Lagrangian and you only need to impose the compact constraints in capital X, which is typically a box. So that's the advantage, and that's what we wanted to compare with. And the overall impression for those who have to leave the room now is that the method is successful, and in presence of multiple local minima, it has the tendency to find the best solutions, the deepest minima. And not only that, it also has the tendency of obtain them more often than when you use Nitro on its own. So more often you can get global minima or deeper minima. We will see it in the examples. The first example is problem 79 from the famous book of Hock and Szytkowski from 1981, which has many examples. Then the dimension is 5, and we have a polynomial optimization problem with equality constraints. We use WK equal 1 over K to the power 6, and our method identified 6 isolated minimizers. And the best of these coincides with the one reported by Hock and Szytkowski, which is this is the best solution that was obtained. Now, here the statistics that here are shown that we run Nitro on its own 30,000 times, and we ran our algorithm 30,000 times, and checked how many times we obtained each of these solutions. So we see that 45% of the times Nitro on its own obtained the best solution, and all the other times it kept playing around, giving the other solutions which are farther than the best value. While our method all the time obtained, all the 30,000 runs obtained this best solution. So this is what I meant when I said that it has, at least in the examples that we run, it has some tendency to obtain the best solution, at least in this example. So in terms of CPU time, I can say that our method, which we call Primal-Dual penalty method, took 5 times longer. But when I say longer here, there are all measures which are less than 1 second. So it's not too long. And another observation which holds for all the numerical experiments is that our method can be made faster if we would establish a larger or coarser epsilon tolerance for the measures of feasibility and optimality, and therefore that would really accelerate the method, at least in iterations. later equations you can use tolerance. And if your original aim, for example, was to find the best solution, the solution with the best optimal value, then neutron on its own would have been expected to be run more than twice, 2 or 3 times to get that solution, while our algorithm would need to be run only once. Okay, the second problem is a first problem which has a history, is the Kissing number problem. The Kissing number problem, let me show you the figure, is the problem of having a central sphere here of radius 1/2, let's say. And the question asked is how many spheres can you place in the space of the central sphere without any overlap? So you don't want to have any overlap. And what is the maximum number that you can fit here without any overlap? This is a very important problem in applications, in packing theory, etc. And it's a very complex problem because it has a lot of possibilities for the possible configurations that you can get here. Observe that if you change the position of the balls in a every rigid translation of the balls in the surface of the central ball gives you a different solution, a different configuration. So the problem, in fact, you see the variables are the center of the spheres that are in the surface. So those centers can be rotated in a rigid way and you get another solution. So for each of those positions, you have a huge number of local minima or local solutions for this problem. Now this problem has many formulations in mathematics, in the literature. Here we use this smooth formulation. This alpha represents the distance between the centers. So if the radius is 1/2, then the ideal distance within the centers is going to be 1 or more, because if alpha is less than 1, then it means that the centers are at a distance less than 1, and this means that the balls are overlapping and your configuration is not a good one. Therefore, you need alpha here to be larger than 1 for it to be a viable configuration. And the Kissing number problem is to find the maximum number p of balls that kiss the surface of the central sphere without them being overlapped. That's the Kissing number problem. And there was this famous discussion between Newton and Jacobi sometime in the 17th century. Newton said that the number was 12. Jacobi said that the number was 13, because I suppose that because there is a space here. And of course, I think Newton was right. Okay, let's go to our situation. Now, as I told you, this has many stationary points, so it's difficult to compute and you may get a lot of local solutions. For n smaller than 4, you have, for n smaller than 4, the Kissing number problem is known. So in particular for n equal 3, I mentioned to you it was 12. However, for n equal 5, 6, and 7, and many others, it's not known. The only thing known are some bounds, upper and lower bounds. So it's known that the number is between these bounds. Therefore, if you use a number here which is smaller than these lower bounds, you should get an alpha which is larger than 1. At least once you should get an alpha which is larger than 1. Amongst of those millions of possibilities, if you get one design which is larger than 1, then you got a viable configuration. And so our aim is not to improve on these bounds, because this is really very hard, but to test the performance of our method and compare it with what Nitro would have done on its own. So in all cases we choose numbers which are smaller than the known bounds. So this should give you alpha greater than 1, right? And here I want to emphasize the number of variables. The number of variables depends on the dimension of the problem. So in this case, the number of variables is 38. times dimension 5. Right, so this is the number of variables, and this is the number of constraints. So it's a huge number of variables, huge number of constraints. Sorry. And here are the results for nitro on its own and our method, Primal-Dual penalty method. So you see that for the small instance, both our method and nitro on its own obtained values of alpha which are valid configurations, alpha larger than 1. However, nitro on its own obtained that less than 1% of the time, and our method obtained that approximately 17% of the time. These percentages were obtained by running each of the approaches 1,000 times with random initial guesses, right? And then for the larger instances, something interesting happens. For the larger instances, nitro on its own can never provide a viable configuration, never. And our method sometimes can provide a viable configuration. So for example, this is a histogram of how many times we got a viable configuration. So here you see that almost 70 times we got a result which was larger than 1. So in many times we got results larger than 1, whilst the green part, which corresponds to nitro on its own, got only these few times got a viable configuration. For the next one, we see that our approach obtained a viable configuration in this region here, while nitro never got a viable configuration. And I just want to emphasize a difference in the behavior. So you see that there are clear maximums, and those maximums are shifted to the right where the target one is. And this shift is even more emphasized for the larger one of the instances in which we get which the maximum number of results happens more shifted to 1. So we got many results which have a viable configuration. Okay, so this is all the observations are the ones that I shown you before. Let's go to the last example. This is an example post and studied by Markov in the end of the 19th century and fully solved by Dubins in 1957 when fully solved in 1967. At the time of Markov, he wanted to know how to construct train tracks. And if you have two cities, so let me show you an example. Suppose that you have these two cities, and at each of the city you have a train track that is incoming with this slope, and another train track which is incoming with this other slope. And of course you don't want to destroy the train track, you want to keep them, so you want to use those existing train tracks and to construct another train track that connects both cities. And how to do this with the minimum length? This is the problem that Markov wanted to solve, and Dubins fully solved in 1957. Yalchinkaya showed in 2017 showed that this can be reformulated as an optimal control problem, and he used the maximum principle to reduce it to a finite dimensional problem, which is this problem that I wrote here. But let's concentrate on the fact that after simplification, this problem can be expressed in terms of psi and for equality constraints. So we use wk equal 1 over k plus 1. So here this is a mistake, so it should be 1 over k. Okay, so the instances that we use is starting at 0 with an angle of minus pi over 3 and finishing at 0.4 with angle minus pi over 6. And one important characteristic of this problem is that you cannot make the turns very sharp. You have to respect some constraints for the curvature. So in the paper by Yalchin-Kaya, he obtained 7 stationary solutions, which are the 7 solutions that I'm showing here. As you see, these are the length of the solutions. So the best possible solution is this solution 1 here, and the statistics here were obtained by running each of the approaches 20,000 times with random initial guesses. So let's go to the results. So Nitro, almost 90% of the time, found solutions larger than 3, while our method found solutions less than 3, 98% of the time. And we would expect to find good quality solutions, like for example, solution 1 and 3, by running our method just once in less than 1 second. And Nitro on its own would be expected to be run about 9 times for the same quality solutions. And as we see from the times, so we have observed that for the time, for the CPU times, when looking at the kissing number problem and this problem here, our method is more time efficient when compared with Nitro, when you have larger instances. So this is the best solution, which was obtained 80% of the time by Nitro and 36% of the time by our method. The second best, 3% of the time, was obtained by Nitro, and 62% of the time was obtained by our method. And for all the others, you see that 89% of the time, these were the solutions obtained by Nitro 89% of the time, and we obtained these solutions only 2% of the time. So conclusion, we analyzed a primal-dual scheme in which instead of having a single dual problem, we have a sequence of those, and establish strong asymptotic duality. We use the theory to define a primal-dual epsilon subgradient method which reduces WK at each iteration and therefore forces the current Lagrangians to approach the classical weighted L1 penalty function. And the primal sequence accumulates at a solution, and if the dual variables happen to be bounded, they converge to a dual solution. Now the open question is, can we consider other types of Lagrangians that smoothly approximate a non-smooth Lagrangian and devise similar asymptotic schemes? Can we avoid the assumption of compactness of X? And what would the numerical experiments be if instead of implementing the pure subgradient method, we implement the epsilon subgradient steps? And can we extend this to semi-infinite programming problems in which we would have to choose only a finite number of constraints at each iteration? Thank you. This is all.
Thank you very much, Regina, for your talk. So if anyone has any questions to our speaker, then you can just unmute yourself or write on the chat. Okay.
Hello, Regina. Okay.
Thank you, Joydeep.
Hello, I want to ask you whether the theory that you have given in this paper, that is in infinite dimensions, right?
Infinite dimensions, yes, in a metric space.
Okay, very general. I want to ask you, when you compute subgradients in actual, when you run the algorithms, how do you actually do? You have the structure of the Lagrangian function or the supergradients, whatever. How do you choose, pick and choose the subgradient, a particular subgradient?
Well, in this case, what you need to do is, in fact, okay, let me go to the convergence analysis. What you need to do is, you need to find the search direction, right?
Yes, yes.
So you need to solve the search direction you need to minimize the Lagrangian. So you need to solve this minimization problem. And this minimization problem, wherever you need to find the element that minimizes this Lagrangian. For example, I will give you a concrete example. Yelchin and I have a PhD student who are applying a similar method, not exactly this one, but a similar one for solving an optimal control problem. So that's an infinite dimensional problem, and that's solved in infinite dimensions. So you have a model, and the solutions of your model are a continuous function, let's say, and it's an optimization problem with ordinary differential equations as constraints and equality constraints. So it's originally a convex problem, but the variables are functions. So you need to minimize, you need to solve that problem in infinite dimensions. So what you do is you write down the optimality conditions in infinite dimensions. So if for example, suppose that you are in a Hilbert space, then you compute your subgradient will be a function, and it has to be a function in a Hilbert space as well, because the subgradient is in the dual space. So you have the primal space, the subgradient is in the dual. So the optimality conditions are an inclusion, let's say, in the dual space, and you find the function that minimizes your problem. So in the particular case that we have with our PhD student, you find the function is a linear function, and you obtain it. So in fact, you have to look at case by case situation, but you can do it. You need to have some calculus power, yes, but it is possible to do it. And when you do it, it's amazing the amount of additional insight that it gives you on the original problem.
Oh, fantastic. Thank you, Regina.
This
is a very nice explanation. Thank you.
Thank you.
So we have another questions, Janos question in the chat, and a follow-up question from Scott as well. So Janos, can you unmute yourself and then?
Yes. Let me just.
Because we're going.
Janos. Yes, Janos. Thank you, Janos, for your question. So, what do you mean by the geometry? Can you explain that to me a little better?
Yeah, can you hear me?
Yes, I can hear you.
Me?
Yes.
Because my computer gave up, so I'm improvising a little bit here. You see, you say that when you have complicated configurations, then your algorithm picks out good solutions much more likely than if you just take a standard solver and apply to the problem. If I understand it correctly, then this Nitro alone is really just a standard solver that does not look into the structure, just apply. And so the question is, probably this relies on Taylor expansions and so on, and it just does what it does. And yours looks at the dual. And by looking at the dual, you seem to end up in a good minimum much more often than a direct solver. And that seems to imply that this Primal-Dual approach understands the geometry of the objective function or of the entire problem much better than a direct solver. And the question is whether you have any intuition like why that might be true, because I don't see it.
Well, in fact, we have a similar question because we think, what we think is the following. You have an original problem, and you have the issue of including the constraints in your calculation, or including the constraints as constraints, or including the constraints in the objective, which is what our method does. So what we do is we take the complicated constraints and we put them in the objective, and we use a powerful way of differentiating that function. So we just differentiate when you differentiate you don't take into account equality and inequality constraints. And when you have to take that into account when you use nitro, that may introduce some trouble that has to do with the fact that the problem is complicated itself, and then nitro cannot deal with so much complexity and also deal with the constraints at the same time. What you are doing is you are allowing nitro to not to worry about the constraints. You are saying, okay, nitro, don't worry about the constraints, just worry about the box constraint capital X and solve what you can by just differentiating. And as you say, use the Taylor whatever. So you allow nitro to forget about the constraints and do what he can do best or she can do best, right? And so I think that from my point of view, that is one of the main advantages of this method. It doesn't have to do necessarily with the geometry, because you change the problem and you'll observe a similar behavior, that you make things simple for the solver. You make life easier for the solver. I think that that's what makes the difference. But of course, I cannot prove that to you. And, and I don't know if somebody can prove that because it really depends also on the problem that you are testing.
Yeah. Is it possible that your parameter, your regularization parameter, gives you a bound on the angle which you can deviate kind of from the in the primal? Then on the angle you can deviate from the gradient or something of that kind, while nitro, when it solves directly, it will also have a relaxation parameter which you don't see, but this will probably be on the constraints themselves. So nitro will have a relaxation on the sets, on the allowed sets, on the admissible sets, while you probably have a relaxation on the angle with the gradient. Is that maybe a possibility?
Look, I don't really know, because there is a relationship between W and so I think that we need to look at this here. So this is the deflection, right? So I really don't know if there is there should be some relationship between maybe WK and DK, which are the guys that you can choose. So WK and DK they are at your service, but PK is not. PK is something that depends on XK, and XK is comes or not, doesn't come. So I don't really know the question. I really don't know, because
it's okay. I see. It's a strange question and not very easy, so I understand. Okay, thank you very much.
No, I hope that what you can try to experiment our method with other types of problems and see what happens. Maybe you may get some intuition. I mean, this is a new method. This is an open table to everybody to try and see with their own examples what's going to happen. I mean, I would be curious to try this even with a convex problem, or even with a problem with the with discrete variables. What would if you try this with discrete variables? What would it do? Would it do better than when you use branch and bound or something like that? Let me see. So there is another question from Scott related with Janos' question. Can you better explain what your algorithm is doing that vanilla nitro is not? Is the difference your Primal-Dual rule, or is the main difference the smooth regularization of the normal unsmooth Lagrangian, or is it both? Okay, so I think that the main difference is, let's look at the algorithm again. So the main difference is that you use nitro only at this point, and you have these box constraints, and you say, okay, nitro, solve this minimization. And this is much easier for nitro than going and solving the minimization with equality. I think that's the main. And also the other difference is the update of the penalty parameters. Here you're updating the penalty parameters not as you like. You don't do a gradual increase of the penalty parameters as it's classically done in L1 penalty. You here are doing a dual update of the penalty parameters. So you are using a very precise algorithm for updating the penalty parameters. And you are using an algorithm which converges. So it's a very precise type of update here, which has a lot of theory behind. There's a lot of convex analysis behind this update. And I think that this is also a main difference. I don't know if that answers your question. And of course, this Lagrangian is smooth. That's another advantage. This Lagrangian is smooth, so you can do it. You can use it with a very efficient solver. If this Lagrangian here would be non-smooth, then you would need to use a non-smooth solver. And the non-smooth solver has a lot of problems, is not as accurate, is not as quick, etc., etc. I don't know if this answers the question.
Yeah, it does. So it sounds like you're saying when you use Nitro Vanilla on its own, you're using it to you're basically pointing it at the complete constrained problem with the constraints on it. Whereas when you're using the PDPM, you're using the box solver just to solve the substep number 2, but you're giving it this regularized, smooth substep, and also you're determining these dual updates in this more precise way. Mm-hmm. If I understood right.
Yes, exactly. Okay. And also it's open. For example, I think that it would be interesting to try this on problems which have integer constraints that can be written as polynomial equality constraints, and see what happens, because at every iteration you would be solving a linear programming problem. Right, so you replace your original problem by a sequence of linear programming problems. So what can happen? I mean, it's interesting. We don't know what will happen.
Thank you, Regina. I have any other question from the audience, from the participants?
May I step in for a minute?
You may.
So, thank you. Thank you very much, first of all, Regina. Indeed, beautiful theory. And as already mentioned by Joydeep, very nice, beautiful presentation.
Thank you.
Beautiful slides. Thank you. One short formal question. In the very beginning, in the setting of the problem, you have a capital X, a set representing non-functional constraints, which is a subset of a metric space Y capital.
Yes.
X capital doesn't play a big role in the whole theory, as far as I understand. You need compactness of it. And capital Y doesn't play, it seems doesn't play any role at all. What is the advantage of separating, subdividing into X and Y?
There is no advantage. In fact, in the paper, we didn't use Y. We just used capital X. However, in general, when you minimize a problem, you don't require your functions to be defined in a compact set. You can have your functions defined in a larger set.
On a bigger.
Yep. But I mean, initially in the paper, in fact, we had X written here, but it's not necessary, because if you place X here, it means that your functions are only defined on X. But they might be defined somewhere larger. That's the only reason for which I put Y here. Nothing else.
Yeah, I'm just
for you to ask me. Just for you to ask me the question.
Thank you. Keep it for your future research as well. Leave something for me to ask a question. Thank you. Thank you again.
You're welcome.
So I have a questions, just like simple questions. So how many times generally you run step 2 again? So because this it will affect the running time of the algorithm. So I like is that in a finite times or a finite number of times or?
You mean in the runs of the algorithms?
Yeah.
Yeah, usually it finishes. Yes, look, let me just show you.
Yeah.
In the numerical experiments here. So with this implementation, you will satisfy the stopping criteria after a finite number of steps.
Yes.
So with this implementation, the algorithm will stop after a finite number of steps. At least this is my understanding. I would like to. I don't know. I think this is the situation. This is what I remember. This is what I remember. I will ask my co-authors to remind me if anybody remembers more than me about this. No, what my recollection is that you arrive at this stopping criterion epsilon after a finite number of steps.
Yep.
And then that's it. Then you finish. You have your solution.
So
yes.
I mean, so okay, so this one is a very general approach. Like if we consider some particular case when some constraint is nonlinear, but actually we can rewrite many of them in a mixed integer linear programming, and then and then run some standard solver, and then this will give you optimal solution. Then comparing to this one, what is advantage if we use this one to solve some particular problem like that?
Look, I don't know because we didn't do experiments with that particular example. I thought about that example because of the conversation that we had about your particular problem that you were studying, and that looked to me like a natural example to try because it would be easy to implement, and because the subproblems will be immensely easier than the constraint problem. So if you have constraints which are integer type of constraints, like x times 1 minus x equal to 0, so that's a very complicated problem very complicated constraint to deal with. While if you put it in as part of the Lagrangian, that complexity is shifted. So you transform your original problem into a sequence of linear programming problems.
Yeah.
So I think that would be interesting to do.
Yeah. So I would just I don't know if it's true or not, but my intuition from your algorithm is that you remove the complicated constraint and then you use Lagrangian so to provide another like approximate by another linear constraint. That means easier constraint. And then the reason why it's work because that provide a lower bound. If this one is a minimization problem, it's a lower bound for the whole problem. And then your stopping criteria is if your solution belong to the Figaro set. So which means that is satisfied. So your approximation is successful for that complicated constraint.
Yes, exactly. So if you minimize and that minimizer happens to be feasible, then that element is a primal solution, and the parameters that you use in the Lagrangian are a dual solution.
Yeah. Okay, thank you very much, Regina, for your beautiful talk.
And thank you everybody who thanked me for the talk. Thank you very much. And Yalchin and Chris and I will be very happy to answer to any question anybody can have. And let's hope that some of you will come up with a nice problem and you will be able to apply this method to your problem.
Yeah, thank you, Regina. So next week we will have another speaker from University of South Australia, which is Yalchin, and looking forward to see everyone there. So at the meantime, take care and have a nice week ahead.
Thank you very much.
Bye-bye. Thank you, Regina.
Thank
You,
very
Han.
much.
Thank you. Bye-bye.
Thank you.